All right, welcome back, mathematicians. We are on to section 4.3 today on monotonic functions and the first derivative test. First, when we mean monotonic, we're kind of talking, if someone's talking in monotone, the voice isn't going up and down and fluctuating. It's just going in one direction. So when we say a monotonic function, we're saying it's either increasing or decreasing over an entire interval, okay? So we can also define it using the derivative. So if we suppose that f is a continuous function on the closed interval a, b, and differentiable on the open interval a, b, then we can say that if f prime is always positive, aka greater than 0, for each point x on the open interval, then we say f is increasing on the closed interval. Similarly, if f prime of x is less than 0 for each point x on AB, f is decreasing on that closed interval, right? Remember how we've talked about before that if f prime of x equals 0 or is undefined, that is a critical point. So if f prime is positive, we're increasing. F prime is negative, we're decreasing. If it's 0, we're a flat line, so we're a critical point. Alrighty, so let's work through an example. And we're asked to find critical points of f of x. That's not all going to fit there. F of x equal to x cubed minus 12x minus 5. And identify we say the open intervals f is increasing. I write I and C, and decreasing, DEC. All right, so first we need to find our critical points. All right, point or points. We don't know how many there are. So we're going to set the derivative equal to 0. So first we need to find the derivative. So power rule, so that's going to be 3x squared minus 12 minus 0. So just 12. All right, and then I can factor 3 out so that I'll get x squared minus 4. I'm going to set this equal to 0. So we'll have 0 equal to 3 x squared minus 4. Divide each side by 3. We just get that 0 is equal to x squared minus 4. And x is equal to 2 and negative 2 plus or minus 2. All right. So I like to make a chart here. That's how I kind of learned how to find the intervals. So I know that these 2 points are when my derivative equals 0. Now I'm looking for where my derivative equals all positives and all negatives. We learned from the intermediate value theorem that a 0 has to be in between a negative number and a positive number. So that's why we find our zeros are roots of the first derivative. So I like to draw this chart. Alrighty, so you're going to write your critical points. So negative 2, and 2. I like to draw them in order as they would be in the number line. And then I draw a line directly below them, because I'm not plugging them into anything quite yet. And then I'm going to choose some x values that are on either side of my critical points. These are what I'm going to use to test the waters. So I'm going to plug these numbers into my derivative to see if I'm positive or negative. So if I plug in, I'm -3 here, a number between -2 and 2, that's going to be 0, and a number greater than 2, choose 3. So we're doing this because remember that when I plug in to the -2 or 2 into the derivative, that's going to give me 0. So any number that's between 0 and 0, if it's positive, it's going to be positive that whole interval. If it's negative, it's negative that whole interval. It can't change because these are the only two spots that the derivative is equal to 0. All right, so then I'm going to take these 3 x values and I'm going to plug them into f prime. All right, I want to know what the graph is doing. I don't care where they are. I want to know what the graph is doing. I care if we're increasing or decreasing. So I go up to f prime of x, and I'm going to plug in -3. Well, -3 squared, that's 9. 9 minus 4 is 5. And times 3, I get a positive 15. All right, cool. Now I'm going to plug in 0. 0 squared is 0, minus 4. Get -4 times 3, a -12. And then for 3, I'm also going to get 15 again. Now I'm going to write down the sign. With practice, I only usually include the sign. And by sign, I mean if this derivative is positive or negative. So usually I'm writing a plus, a minus, and a plus. And then you write down the behavior. So I know from my definition up here, if my derivative is positive, the graph, the original, is increasing. If we're negative, we're decreasing. And then we're increasing again. All right? So that's what this whole chart tells me. So we can write behavior. And sometimes I even just kind of like to draw like a little visual. I'm increasing, I'm decreasing, and I'm increasing. And we'll get to why this is important later on when we get closer to figuring out the first derivative test. So then you're going to come down here and write, you can't just give me a chart as an answer. So we're going to say we're increasing on, so this -2 here, I'm increasing all the way down into negative infinity, right? I'm not quite sure. Yeah, this function has no problem plugging in. Its domain is all real numbers. So we're going to go all the way to negative infinity for this first interval. And all the way to -2. And then our second interval from 2 is going to go, it's going to keep increasing to infinity. So 2, comma, infinity. These are all open intervals because we're not including -2 and 2 because those derivatives are 0. Our definition said increasing was strictly positive, not including 0. Okay? And then decreasing on -2 and 2. Alrighty, awesome. So this kind of chart and finding where we're increasing and decreasing allows us to identify local extrema. So all right, so I'm going to draw graph as best as I can. And we're going to start down here. Great. So you can see that we have a critical point right here, 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 and we kind of don't have a horizontal tangent there. We actually have that f prime is undefined, right? Because that's a cusp, right? U and D for undefined. All right, and then I can kind of split these intervals from endpoint to critical point to critical point to critical point. So what I mean by that is I can take this, slice it, make another slice, and another. Can I move this over? Neat. All right, cool. And so the point of this is to show you guys where f prime is going to be positive, negative. So we're increasing on this whole first section. So f prime is greater than 0, and I'm still increasing. F prime is greater than 0. Then I'm decreasing. F prime less than 0. We're increasing again. F prime greater than 0, and then decreasing. F prime less than 0. All right, cool. So notice that I have a absolute max here where f is undefined. I have an absolute minimum here. And then I have local extrema here and at my endpoints. Notice I don't have one at this little guy right here. The reason is because f prime is positive and then it continues to be positive. So it's on the left-hand side, everything's smaller than it. On the right-hand side, everything's bigger than it. So it's not any type of extrema. So this leads to the first derivative test. You can see at this blue point right here that I'm increasing then decreasing. That gave me a maximum. Then I was decreasing then increasing. That gave me my minimum. Increasing then decreasing, and I got my absolute max. So that's kind of the general idea of the first derivative test. And now we're going to write it a little nicer. And it helps us find local extrema. Right, we already have a process to find absolute. Alrighty, so we're first going to suppose, we get our bearings, that C is a critical point. So first outcome of the first derivative test is if f prime changes from negative to positive at C, f has a local, what do you think it is? It's going to be a local minimum. At C, right? So we can look up at our beautiful drawing that I've done, and when we were decreasing, we're going down the valley, then back up, negative, then positive. That gave us a minimum. Second outcome is the opposite. So if f prime changes from positive to negative at C, f has a local maximum. at C. And then we have a third option that if f prime doesn't change sign, so if it's negative, negative, positive, positive, then f has no extrema at C. All right, so let's do another problem now knowing we know about the first derivative test. So make sure this isn't numbered. Okay, perfect. So we are going to find the critical points of f and identify the intervals it's increasing and decreasing. Then find all local and absolute extrema. A big to-do list, but we can do it. Alrighty? So, alright, and f of x equals x squared minus 3 times e to the x. All right, so the first thing we're asked to do is find the critical points. So we're going to take the derivative and set it equal to 0. That's how we find critical points. So f prime of x, I have a function of x times another function of x. So I'm going to do product rule. So 2x, took the derivative of x squared minus 3, and I'm going to keep e to the x plus keep x squared minus 3, take the derivative of e to the x, which is just e to the x. I also like to simplify things. It makes my life a lot easier when setting things equal to 0. I pull out an e to the x from each term. And then again, I'm just going to write this how I really like to look at polynomials. And we usually write them in decreasing powers. All right, so we need to set this equal to 0. So from last lecture, we talked about how an exponential function cannot equal 0. Anything to n power can't equal 0. So I'm just to divide e to the x over, and I don't have to worry about it at all. So I'm gonna have 0 equal to x squared plus 2x minus 3. And then I can go ahead and factor that, and that's going to be x plus 3 minus 1, right? 3 times negative 1 is negative 3, and they add to positive 2. Okay, cool. So that means my critical points are x equals 1 and x equals negative 3. Technically, those aren't points, they're just x values. So we're now going to identify the intervals. It's increasing and decreasing. So now we're going to make our little chart. So negative 3, 1, Draw a line under it. A number less than 3, I'm going to choose -4. A number between -3 and 1, I usually like to choose 0. It's pretty easy to always plug in. And 2. So we're going to call that x. And, okay. And I know I can simplify the first derivative up here to be e to the x plus 3, x minus 1. I find that easier to plug in numbers if they're factored. So I am just going to do the sign of f prime of x. I just find that to be faster than plugging in a number. I kind of only care about the sign. E to the x, so let's rewrite what f prime of x is down here, so I don't have to keep looking up. X plus 3, x minus 1, okay, great. So I plug in -4. This is always going to be positive no matter what number I plug in. -4 plus 3 is going to give me -1, and then -4 minus 1 is going to be -5. So a positive times a negative times a negative is going to give me a positive number. All right, so f prime of -4 gives me a positive times the negative times the negative. Okay. F prime of 0, it's going to give me a positive times a positive times a negative. It's a negative. F prime of 2, that's going to give me a positive, positive, and a positive. And that'll give me a positive number. Is that clear how I do that? Not everyone does it this way. I just like it this way. That's how it works best for me. Bailey will do more examples on his video, so I would definitely check that out, and it'll totally help. So then, going to write down the behavior. So I'm increasing, and then decreasing, and then increasing. So I'm going to scroll down, and then I'm going to write it, because I'm going to write under that chart again. So we're increasing on -infinity to -3 and 1 to infinity. All right. Remember, the derivative can only change signs if it first intersects 0. And since these are the only 2 points that intersect 0 at -3 and 1, all the way towards positive infinity, it's going to be increasing, and then all the way towards negative infinity, it's increasing. So, and then we're going to be decreasing from -3 to 1. Perfect. So now I also like to draw those lines, remember? So I used to draw increasing. Oh, wait. Maybe if I drew them right. You can see. Oh my gosh. Okay, yeah. Increasing, decreasing, increasing. This makes it really clear visually that -3 is a local max and 1 is a local min. The first derivative test, you can memorize that all you want, but you need to understand if I'm going up, then down, I was at the top of the mountain, I'm at the max. If I'm going down the hill, then up a hill, I was in a valley. I was at my minimum. I looked at all these pictures. Pictures are key to this, because then we're going to get on to curve sketching. And I'm going to give you an equation. You're going to have all these tools, and you're going to be able to draw a picture for me. Okay, sorry, I dropped my notebook. So then we can say, find all local and absolute extrema. Cool. So I know I have a local max at -3, f of -3, which is, I don't feel like doing that. And we'll have a local min at 1, and if I plug in f of 1. So what about absolute extrema, right? We're not given any endpoints here. We're just given a function. I can plug any number into f of x. So the whole domain and range is like, there's no endpoints here. Notice that in my picture that I drew under the chart, I'm increasing. I don't know if I'm increasing up to infinity or there is a horizontal asymptote. I don't know. But we can investigate that, and that'll tell us if there's any absolute maxes or mins. So I'm going to make a note that I'm checking for asymptotes. Specifically, horizontal ones. Okie dokie. So we're going to check the limit as x goes to infinity of e to the x squared minus 3. Well, e to the x as x goes to infinity, that's going to get really big. Well, as x squared minus 3, that's also going to get really, really big. So there's nothing kind of stopping and halting this from getting really, really big. So that's going to go towards infinity. Big number times big number. What about the limit as x goes to negative infinity? Alrighty, so, well, I know that as e goes, e to the x as x goes to infinity, that's going to go to 0. And exponential functions grow a lot faster than power functions. So even though this bit is going towards infinity, this e to the x is beating it out. Exponential growth is a lot stronger than a power. So this 0, it's like 0 times like a tiny infinity. And that's how we get 0. All right, so this is actually really helpful figuring out if any of these are absolute mins and maxes. I hope that exponential and power function makes sense. Okay, cool. So now let's figure out what these points actually are. If I plug in -3 into f, what do I get? 9 minus 3, what's 6? So I get 6e to the -3. And 1. One squared minus 3 is what? 2? Yeah, no, -2. -2, e, just e. Okay, cool. So if my graph to the left-hand side is going to be at most 0, and on the right-hand side, it's going to go up towards infinity. When I have something infinity, that means that my local max, it's just going to be a local max. I can probably plug in like 100 and find a number bigger than my local max. But it's just a local, it doesn't mean it's not a max anymore, okay? But my local minimum, as long as it's less than this asymptote, it's going to be an absolute minimum. Okay? because this is, I'm approaching 0. So either my minimum can't be decreasing down to it. We saw that. Right, we're increasing, going this direction. But if I'm going this direction, the other way, I'm going to be decreasing. So I hope that makes sense. I'll draw a picture of what this graph looks like to kind of describe what I'm saying. So I can never spell asymptote right. All right, so now I have an absolute min at 1, -2e. Perfect. Another way to have done this is if we didn't have the knowledge of horizontal asymptotes, we could have just plugged in a really, really big x value on the negative end and the positive end. So like 100 or like a -100. On tests and quizzes, you aren't going to be able to use your calculator, so that's why you have the knowledge of horizontal asymptotes. All right, so let me draw a picture of this graph to kind of show you what I'm saying about how the horizontal asymptote allows the minimum to exist. So let's make the minimum down here. And that's at 1, and at 1, 2, 3, I have a max at, it's like a positive number, I think. We'll make it right there. Okay, cool. So after 1, we were increasing. Between -3 and 1, we were decreasing. And then we were increasing from -infinity to -3. So it kind of looks something like that. That is a terrible picture. But what I'm saying is this horizontal asymptote makes these numbers go down, down, down to 0. If I'm going towards the other way, even though, well, what you can see with that interval is increasing. It's increasing as we're going this way, but I'm talking about as x goes towards -infinity. So we're kind of swapped. It might be confusing you right now, and I'm so sorry. I'm just showing you a way to think about it. We'll get into more graph drawing later on. So let's do a problem from your textbook. It is problem 30 from this section, and I want to make sure that, yeah, okay, cool. So example 4.3.30. Boing. Okay, cool. We were first asked, well, first we're given that k of t equals 15t cubed minus t to the 5th. So we're first asked to find the open interval or intervals on which kt is increasing, oops, and decreasing. Alrighty, so we're gonna find our critical points. So we need to find k prime of t. So Did I write this down right? Interesting. Okay, cool. So then power rule says this is going to be 45 t squared. I noticed in my notes that when I tried to do this, I missed a number, and so my numbers are all funky. Okay, cool. So 45 t squared minus 5t to the fourth. Beautiful. Let's simplify that. Everything can be pulled out by a 5 and a t squared. And then 45, what is that? 9? Yeah. 9 minus t squared. Oh my gosh, these numbers are a lot better than what I was working with. Okay, cool. And then if we set this equal to 0, so we know from algebra that either 5t squared equals 0 or 9 minus t squared equals 0. So 0 equals 5t squared, and 9 minus t squared equals 0. So we'll do 5t squared. So divide by 5 and I get 0 equals t squared, or that t equals 0. And then I can add 9, so then I get that t is 3 and negative 3. Beautiful. These numbers are so much better than I was dealing with. I was dealing with like 2 over root 5 earlier. A simple little math mistake. Okay, cool. So now we're going to make our chart. So we'll do negative 3, 0, and 3. Draw lines. You don't have to make this chart if you don't want to. This is how the textbook has it, and this is also how I learned it. Okay, cool. So we're going to pick some x values. Negative 4, negative 1, 1, and 4. And now I'm going to plug into, I'm going to simplify this to 5t squared, 3 plus t, 3 minus t. Okay. So when I plug in negative 4, I'm going to get a positive number, a negative number, and a positive number. Wait a second. Yeah, that's right. Right, okay, cool. So that's supposed to be negative. Right, because we'll get 5t squared will always give us a positive number, negative 4, 9 minus 16. Yeah, no, that's a negative number. Oh my gosh, brain fart. Okay. So we'll have a negative number there. And then at negative 1, I'll have a positive. Positive 1, I'll have a positive. And then at 4, I'll have a negative again. So I am decreasing, increasing, increasing, and decreasing. So we're just finding our open intervals right now. We're increasing and decreasing. So we're increasing on negative 3 to 0 and 0 to 3. We're not increasing at 0. So that's why we're not including it. Sometimes people include 0. I don't. Because there's phrases called increasing and strictly increasing. Some people can say a constant number is increasing. I disagree. So then we're going to be decreasing negative infinity to negative 3 and from 3 to infinity. All right. So then part B, asked to identify the functions local and absolute extrema. Well, with our handy dandy chart, we can go back and see that we are decreasing, then increasing, then increasing, and decreasing. So that makes 0 nothing. But it makes -3, we can see a min, and +3, a max. So local max is going to be 3. What is k of 3? 3 cubed is 9 times 3, 27. Times 15 minus 3 to the 5th, so 163. No, wait, 62. Okay. And then our local min ooh, that should have been a -3. Okay, hold on. So 3, 162. And then -3, because that changes it. Because it would be 15 times 27. And then instead of minus, it'll be a plus. So plus 3 to the 5th power. Okay, yeah, duh. -162. Hold on. Oh, duh. Getting my head all unraveled. So my max is at +3, and my local min is at -3. What was I thinking? Okay. So sorry. So that can happen where a local min can be smaller than your local max. Okay. So now we need to see if they're absolute. Well, I know on one end we're increasing or we're decreasing all the way from, I don't know how big that was, and then we're decreasing down again. So if I look at the end results of KT, which is 15t cubed minus t to the 5. This is going to keep going down to -infinity, right? Because that t to the 5th is going to be a lot stronger than t to the 3rd. And then the limit as x goes to -infinity, 15t cubed minus t to the 5th. Well, that's going to go towards +infinity, which we can also see by looking at that we're decreasing. So if I'm decreasing from 3 to -infinity, that makes sense that the limit as x goes to infinity is going to be -infinity. It'd be weird if it was infinity, that I was somehow decreasing to positive infinity. That doesn't make sense. And since I'm decreasing from negative infinity to -3, I needed to be decreasing from somewhere. Positive infinity. I can't decrease from negative infinity. Okay? So that's it for this section. We're going to talk about a lot more about curve sketching next section, 4.4, and we're going to learn a lot more about different ways to characterize functions. All right? See you there.